Section 5.5. Because of the fundamental theorem, it's important to be able to find antiderivatives. But our anti-differentiation formulas don't tell us how to evaluate integrals such as the following. The integral of 2x times the square root of 1 plus x squared dx. To find this integral, we use the problem-solving strategy of introducing something extra. Here, the something extra is a new variable. We exchange from the variable x to a new variable u. Suppose that we let u be the quantity under the root sign in number 1 where u is equal to 1 plus x squared. So I'm going to take a look here. You can see here we're going to let u, so this will be the first step here. We're going to let u equal 1 plus x squared. Okay, and then the differential of u is du, which is equal to 2x dx. So that means that when we take the derivative of the left side, we get du. And when we take the derivative of the right side, the derivative of 1 is 0. The derivative of x squared is 2x. And that's going to be 2x dx, which is exactly what they say right here. Now notice that if the dx in the notation for an integral were to be interpreted as a differential, then the differential 2x dx would occur in 1. And so formally, without justifying our calculation, we can write the following. So what that means here is the following, okay? So we convert in the next step here. So when we go from this step to this step, we have the square root of 1 plus x squared, and then we shifted the 2x over next to the dx, okay? And so what do we know? Well, there's a couple things that we know. One of them is that u is equal to 1 plus x squared. So knowing that u is equal to 1 plus x squared, well, you can see here that this 1 plus x squared here underneath the radical now becomes u. Okay, and then we also know the following. We also know that du is going to equal 2x dx. So as we converted this 2x dx here, we can see that du now becomes 2x dx. And now this all becomes just square root of u du. Okay, now when we take the antiderivative of that, okay, which is step 2, well, we know the antiderivative, this is the same thing as the integral of u to the 1/2 du, which is then becomes 2/3 u to the 3/2 plus c. And so we can see here now that when we find this antiderivative, we get this result, which is here. Okay, and then what we do is now we know what u represents. Okay, so u represents the following. So we see that u equals 1 plus x squared, or x squared plus 1, and then we bring that u back into that function to then get 2/3 times x squared plus 1 to the 3/2 plus c. Okay, so, but now we can check that we have the correct answer by using the chain rule to differentiate the final function of equation 2. So if we take the derivative with respect to x of 2/3 x squared plus 1 to the 3/2 plus c, well, we take this and take 2/3 times 3/2, which is x squared plus 1, 3/2 minus 1 gives us 1/2 to the exponent, times 2x, which is the derivative of what's inside. So we end up getting 2x times the square root of x squared plus 1. So in general, this method works for whenever we have an integral that we can write in the form of f of g of x times g prime of x dx. And observe that if f prime is equal to f, then we would say equation 3, that the integral of f prime of g of x times g prime of x dx is equal to f of g of x plus c. And then because by the chain rule, we would say that the derivative with respect to x of f of g of x is going to equal f prime of g of x, g prime of x. Now, if we make the change of variable or substitution u is equal to g of x, then from equation 3, then we would have the following. We can rewrite this now as f prime of g of x, g prime of x dx, which is the integral of that, becomes f of g of x plus c, which is equal to f of u plus c, which is the integral of f prime of u du. Or by writing f prime is equal to f, then we would get the following. The integral of f of g of x times g prime of x dx is equal to the integral of f of u du. Thus we have proved the following rule. So, number 4, the substitution rule. If u is equal to g of x is a differentiable function, which is important that it's differentiable, whose range is in the interval I and f is continuous on I, then the integral of f of g of x times g prime of x dx is equal to the integral of f of u du. And notice that the substitution rule for integration was proved using a chain rule for differentiation. Notice also that if u is equal to g of x and du is equal to g prime of x dx, so a way to remember the substitution rule is to think of dx and du in equation 4 as differentials. Thus, the substitution rule says it is permissible to operate with dx and du after integral signs as if they were differentials.